Ouais, c'est toujours beau. Ouais. Mais donc, on va le préparer.
Pour être sûr que. En fait. Oui, oui. Bonjour. Oui.
Comment?
Sorry, stream.
It's all right. Okay.
You have.
We have yes, almost 2 minutes. No, outline, come up, try volume 2. I don't think that people want to steal the budget. But during the break, when I go for the results, I wanted to get some folders. So those because there's the public described later, there's no folders, so to have extra folders. And I think you also have the ways for me to. Okay. Yes, that are foreigners.
Every time
To connect. But you have an audio.
Yes, I have. But this is the one.
Ah, this is the next.
Ah, oui.
J'ai oublié de savoir si ton compagnon vous avez vu, il pouvait.
En fait, il travaille à Milano.
Ah, d'accord.
Il est à l'INRIA.
Ouais, d'accord.
Donc, il m'a juste amené. Mais non, il a rendez-vous avec Et comme ça tombait bien. J'étais droite.
Ah, super.
Voilà.
D'accord. Il y a un moment, tu as dirigé une thèse au Mexique
Oui.
et tu étais venu à la Outla.
Ah, d'accord. Et tu étais là.
Oui, oui, après il y a eu un workshop, donc j'avais assisté au workshop.
Voilà.
Ça fait un moment.
Oui, mais j'avais beaucoup aimé. C'était beau.
Oui.
Tu es originaire de Puebla?
Oui.
Ah. Et tu connais Claudia?
Bien sûr, oui. Parce qu'à ce moment-là, j'ai participé au programme de la Outla et donc je la connais bien.
Ah, parce qu'elle était super.
Oui.
J'aimerais bien la revoir.
Oui, elle s'est installée à Puebla.
Oui, parce que de temps en temps, on s'échange de mails.
Très bien.
Je crois qu'elle a 2 petites filles.
Oui, maintenant, le temps est passé.
C'était fantastique cette thèse.
Oui.
Je connaissais pas le Mexique.
Ah, d'accord, donc c'était une découverte. Oui, c'est...
En arrivant, c'était l'hiver, on arrive au Mexique, il faisait beau.
Oui. Et il y avait David Sol.
David, oui,
Il est à Tecnológico de Monterrey.
Et puis il est venu à l'INSA.
Si, voilà, oui. Parce que j'ai 2 étudiants en codirection. Et donc, quand il était là, oui.
Ah oui, ça fait longtemps, là, Claudia.
Oui, en fait, le temps.
Ça fait temps, je dirais 2005, 2004.
Oui, à peu près.
Donc, il y a 10 ans. Donc avant, tu étais à Puebla?
Alors, je suis au CNRS, mais nous avons eu une coopération avec le Mexique. Et donc, il y a une unité mixte internationale. Je fais pas mal de... Bah, je me plains pas.
Ah oui, moi j'ai adoré Puebla et Cholula.
Oui, Cholula est fantastique. Moi, j'adore Cholula.
C'était magique. Et puis Claudia était vraiment... C'était très agréable de travailler avec elle. Oui. Ah, je lui enverrai un petit mail.
Oui, voilà. Je veux voir si les autres cuisiniers ne se sont pas égarés.
Cheguei lá, e aí, todo dia mais para Vuol dire che tu già io adesso
No, sí, well, it's 2 minutes after 9, so we're going to start while the others continue arriving. Thank you very much for attending our school. It is with great pleasure that I say welcome to those that come from far away, and also for those that are coming from France. As you know, the objective of the school is double. We want, of course, to share with the students working on related topics on smart cities and big data, the knowledge of our speakers, but the objective is also to strengthen the collaboration relationships that we have with Brazil around these topics. We are an important region in France, and we think that it is very important that we try to start projects and share students and have an active, more active collaboration with Brazil. I want to thank, before I introduce our speaker, I want to thank the Brazilian and French institutions that have supported us, because it was a bit challenging to organize a school with a few time ahead. First of all, for Brazilian institutions, we were supported by University of Pernambuco, by Federal Institute of Rio Grande do Norte, and by the Institute Caesar. Of course, the CAPES and all the other institutions that support research in Brazil have been there. And in France, we have a concrete laboratory that works here in Grenoble, Delicia, that has been very supportive with our action. And of course, Grenoble University, our Laboratory of Informatics of Grenoble, who have been also there for organizing our school. We have connected people on YouTube, so do not think that we're just these few people. Others are coming physically, but the others are there in Brazil following the courses, which also will be online for those that want to see them again. So thank you very much for attending the school. And now I want to introduce Professor Christine Solnon, who comes from the LIRIS lab. She's professor at Grand Lyon, and she's been working on the smart cities, on time-dependent and stochastic optimization. And so let's welcome her, and thank you very much for accepting coming to Grenoble.
Well, thank you for the invitation. It's a great pleasure to speak with Brazilian people. Actually, Penelope is coming from Brazil.
We all have connections with Brazil.
So this is a joint work with quite a lot of people from IBM, Penelope and Philippe Laborie, and also people from the Licit lab, which is a lab on transportation, so Romain Villot and Noureddin El Fawzi. Also other people from l'IRIS, Serge Fenet and Julien Salotier, and finally people from Belgium, Yves Deville and Michael Saint-Guillain. So this is difficult to have a definition of smart cities. My definition, which is a narrow one, is we have a lot of sensors which measures many different things, speed, temperature, noise, light, anything you want to measure. And then we have data flows, and we can use these data flows to make our cities a bit more intelligent. And to do that, we have to analyze the data. And we have 3 levels of data analytics. The first level is descriptive analytics. The idea is to have a summary of data which give a condensed view of the data, use some statistic. Well, we can speak of knowledge, and it is data mining. And the kind of question we can answer with this is, are there traffic jams just right now? Now, the next level is predictive analytics. The idea is to build models in order to forecast what might happen in the future. For example, will the traffic jams happen in the next 30 minutes? And we use machine learning techniques to do predictive analytics. And finally, the last step is prescriptive analytics. The idea now is to use descriptive and predictive to be able to recommend courses of action and help people to take decisions. For example, help them to find the quickest way to go from one place to another place in the future. So in this talk, I'm going to talk mainly about prescriptive analytics. And in this case, we have kind of optimization problems to solve. But I will also talk a little bit of predictive analytics, because to do prescriptive analytics, we need to have models that are able to predict the future. So we also use predictive analytics to do prescriptive analytics. All this work has started within the context of this project, the Optimod'Lyon project. So Lyon is the city very close to Grenoble, a big city. It's the second largest one in France. Well, more than 1 million inhabitants. I guess compared to big Brazilian cities, it's not so big, but in France, it's a big city. So as all big cities, we have problems for transportations. We have a lot of traffic jams. This is the specialty of Lyon. So this project was, the goal of this project was to solve these transportation problems. The leader of the project is the Grand Lyon. Grand Lyon is the set of all cities all around Lyon. And there are a lot of partners, of course, Lyon and Grand Lyon. There are companies, and all this work has been done with IBM. And there are research institutes, including Iris and Let, which have worked on this. So the project is finishing, it will officially be finished in 2 months. And here is an overview of the project. So the first step is to collect different kinds of data about mobility. And all these data are available on a platform. I will give the URL where you can find all these data. And then using this data, there are 3 big services which are available to everybody. The first service on the top is to give a prediction of the traffic in 1 hour. So you have a map and you can see, well, what will be the condition of the traffic in 1 hour. The second service is to allow everybody to have this prediction on mobile applications. And together with this prediction, you have an application which helps you to find the quickest way to go from one point to the other point using any kind of transportation, public transportation, bicycles, car, etc. And finally, the third service here is to optimize urban deliveries. And this is on this particular point that I am working. So here is the plan of the talk. In the first part, I'm going to speak about these smart deliveries. And to do this, I will introduce time-dependent optimization. And then I will talk of a project which is starting just right now and which is the next step of Optimod'Lyon. And this project is called Astral. And the goal of this project is to do descriptive and predictive analytics of traffic data. And finally, I will talk about stochastic optimization, where we try to use not only average predictions, but to use the whole, probability distributions to have more clever optimization. So first, smart deliveries. So everybody knows the problem of deliveries. You have, usually you have a depot, and then you have a set of points to deliver, and you have to find the quickest way to start from the depot, which is not red actually, and deliver all green points, and finally come back to the depot, and of course minimize the total duration of the route. So the first step is to find a model to define this problem, and this model is based on graphs. So we associate a vertex with each delivery point, and then we have to compute shortest path between every pair of points. And the thing to notice is that this is not necessarily symmetric. That is, the time needed to go from one point to the other may be different one from this way, from this way. So we have non-symmetric costs, and these costs correspond to durations to go from one point to the other. So we compute all these shortest paths for all couples of vertices, and we obtain a complete directed weighted graph. Okay, and now it's very easy to solve the problem. We have to solve what we call the traveling salesman problem, TSP, and this is the asymmetric TSP, because we don't have the same weight in this way or in this way. And once we have solved the TSP, we can project the solution here on the map. So this is a very well-known problem. And finally, what is difficult here? So I'm going to develop the challenges of this problem. The first challenge is that we have a lot of side constraints to integrate to this TSP. Actually, when we solve delivery problems, we always have side constraints. For example, we have time windows. A delivery must be done between, I don't know, 8 a.m. and 10 a.m. So this is a time window constraint. We also have pickup and delivery constraints. That is, we first have to go to a first place to pick up something, and then we have to go to a second place to deliver this thing. We also have load constraints related to the trucks. There is some order of the load in the truck, and so we must first go somewhere and finally somewhere. So to take all these side constraints into account, it's not always easy with the state-of-the-art approaches for the TSP. There is a great approach which is called Concord, which works very well on symmetric TSP, and it is based on integer linear programming, and it is able to solve the TSP for very large instances. But it's not always straightforward to integrate side constraints, because these side constraints are not always linear constraints. Also, the other kinds of approaches which works well for the TSP, local search or on-colony optimization, it's not always easy to integrate side constraints. So our proposal is to use constraint programming. I don't know if you know constraint programming. The basic idea of constraint programming is to integrate generic algorithm based on constraint propagation into modeling languages, which are constraint-based modeling languages. So the motto of constraint programming is the user states the problem and the computer solves it. Well, does not always works as well as that, but that's our motto. Constraint programming is competitive with state-of-the-art approaches for the TSP for medium-sized instances, up to 100 vertices. Well, it's competitive. And actually, for delivery problems, we never have more than 100 points to deliver. So constraint programming is a nice solution for this problem, because it's very easy to integrate side constraints. And every constraint you add to the problem actually helps you solving the problem, because we propagate the constraints and it reduces the search space. So constraints are welcomed. Just to show you what is a CP model, here is the CP model for the traveling salesman problem, expressed with IBM OPL, which is the modeling language of IBM. So always a CP model is always in three parts. The first part, we just describe the input data. So here we have a range of stops to deliver. Each stop is a delivery point. And we have costs associated with pairs of costs, pairs of stops, which just tell us how long it takes to go from one stop to the other stop. Then we have to declare the variables, and together with the variables, we declare the domains. So a variable in constraint programming is a mathematical variable. This is just an unknown. This is what we want to solve. So here we have two different kinds of variables. We have the pos variables, which actually solve the TSP and tells us you first have, well, pos of I gives us the highest visited vertex. So it gives us the order of visiting the vertices. And the second kind of variable is the time variables, which simply tells us at what time we arrive on a vertex. And the last part of the model declare what is the objective function to optimize. Here we want to minimize the time where when we arrive on the last vertex. And we give the constraints. So the first constraint is that we must start from the initial vertex, which is this one. And then we say that we leave this vertex at the initial time. And we say that the last visited vertex, we arrive at time v final, which is the time we want to minimize. Of course, all the positions must be different. And finally, this constraint simply says that, to go from the highest vertex to the i+1 vertex, the time needed to travel, we have to add it from vertex to the other one. So this is quite easy to understand, this kind of model. You simply have to write this, and you give this to IBM solver, and the IBM solver will give you the answer. So now it's easy to handle in this model, there are no side constraints, but any side constraint is very easy to add. You just have to add your side constraints here. So this is easy to add side constraints. Now, the second challenge of this problem, which is actually the biggest challenge for us, is that we want to exploit time-dependent forecastings. In the classical TSP, the time to go from one point to the other one is constant, whatever the starting time. And this is not, this is the case when you travel not in cities, but in the cities, we know that the time to go from one point to the other depends strongly on the time you start. And for example, if you leave at 6 in the morning, you usually drive much faster than if you leave at 8 in the morning, which is usually the peak of the congestion is maximum. So now our cost transition matrix is, I don't have a pointer or something?
There's a pointer. Well, it's
good. Thank you. So now to go from U to V, we have a third parameter, which is the time at which we leave vertex U, and it will vary during time. So the first step is to compute shortest time-dependent path. And this is quite easy to do if we have this FIFO property. This FIFO property just tells us that if we leave TI sooner, then we arrive sooner. And this is the case usually. It means, you never have better wait somewhere. And if you wait somewhere, you cannot arrive sooner. The sooner you leave and the sooner you arrive, okay? And this property FIFO is usually satisfied in our urban context, so we use it. And in this case, we can adapt the Dijkstra algorithm to compute shortest path. If it is not satisfied, actually the problem becomes NP hard. So this is a good news that FIFO property is actually satisfied. So we have, the first step is that we have built benchmarks of time-dependent asymmetric traveling salesman problem using data from the Grand Lyon. So here is the address to find all these data. So we have more than 600 loops on roads, and these loops on roads measure occupancy rates and flow, and from these measures we can build speed every 6 minutes, so the time step is of 6 minutes, and from this we have interpolate the average speed on all sections in the Grand Lyon, so it is 50,000 sections of roads, and every 6 minutes we have the average speed on these sections of road. So we have built this benchmark. We have considered 255 delivery points. So this is a map of Lyon. We can see here the peripheric. And these are real delivery points. And for every couple of delivery points, we have, and every time step, possible time step, we have computed the shortest path to go from one point to the other. It's not perfect. Actually, I think this is the first time we have a benchmark which is built on real data for this asymmetric time-dependent TSP. But what is not really realistic is that we have supposed that the time to go from one point to the other, if we have several sections of roads, we just add all the times for these sections. And everybody who knows, well, if you have already drive in a city, you know that when you have to turn left, for example, you have to wait quite a long time. And we don't integrate this in our model, because we don't know when we have to turn left or when we have to turn right. So we simply suppose that the duration of a path is the sum of section durations. So this is a bit naive, we know it. Anyway, it allows us to have a first benchmark. So we have added different kinds of site constraints. We have added the delivery time windows and precedence constraints. And so you can download this benchmark here. And here are a few examples of predicted durations for 4 different origin and destination couples. And so we can see here is it is 7:30 in the morning, and here it is 11:30 in the morning. And here you have the travel time, and so you can see the peak here, which is around 8:30 in the morning. And for some cases, we have two peaks. So we have quite different predicted durations from one path to the other. Now, the first question we wanted to address is it worth exploiting this time-dependent data? Can we compute better tools if we use this time-dependent data instead of simply using average data? For example, here, we have tried either to consider maximum data or median data or average data. And in the next slide, we compare the two obtained on static data. Static data means that we take the median value for each path, and we solve the TSP on this static data. We obtain an order, and of course, we look the time needed to realize this tool on our time-dependent data. So we compare this time with the tool we compute on time-dependent data. In some cases, we compute exactly the same tool. And if we look at the data here, for example, if we have to deliver this point, points which are on a circle like this, well, you will always compute the same tool. If the quickest tool will always be a circle. Okay, you see what I mean? So in this case, you don't. The gain is equal to 0%. So here, each point corresponds to a different instance, so a set of points to deliver. And for example, if I look at this one, here, this is, I have computed a tour on static data, and I have computed the tour on time-dependent data, and for this point, the tour computed on time-dependent data is 6% quicker than on static data. And this, I don't remember, it was maybe this one. And here is the congestion rate. The congestion rate is the difference between the longest time and the smallest time. Here we have a congestion rate of, when we go from 2,000 to 3,000, so it is a 50% congestion rate. When you have a 100 congestion rate, it means that here, during the congestion period, it takes twice longer than when there is no congestion at all. So what we can see exploiting time-dependent data. Of course, if the congestion rate is equal to 0%, you will always compute the same tools with static data and time-dependent data, because well, time-dependent data will be constant. And the more you increase the congestion rate, and the more you can improve the tools by exploiting time-dependent data. Not sure I'm very clear on that. It's okay. Okay, so well, what was a bit surprising, but finally it's understandable, is that in some cases you don't win anything by exploiting time-dependent data, but in some other cases you can actually win. Well, even up to here you have 16% quicker when exploiting time-dependent data, and in this case it's interesting. And actually, when talking with professionals of deliveries, they told us that even 5% is very important for them, because it means a lot of saving a lot of time, but also a lot of gas consumption, so it's important. So, okay, it is worth exploiting time-dependent data. So we can go on this idea. And now, how can we integrate this information in our CP model? Well, it is very simply to integrate. We just have to declare how many time windows we have here. So we have 6 minutes time steps. And to add to our cost matrix a third dimension, which just tells us which time window we are. For the variables, we have to add a variable which tells us, well, this stop belongs to this time window. So we leave this stop at a certain time, and this time corresponds to a time window. We have fixed the duration of the time windows, which is 6 minutes. And finally, we only have to add one constraint, which gives the relation between a time window and a time. So simply we have to divide the time by the size of the time window to obtain the time window. And here we add the third dimension. So this is very easy to model. And now the next question is it efficient to solve? And actually the answer is no, not really. If we simply give this model to the IBM solver, it does not scale well. So that was the starting point of the PhD thesis of Penelope. We asked her to design propagation algorithms which are dedicated to this time-dependent data. So the basic idea of CP solvers is branch and bound. I guess everybody knows branch and bound. And it is combined with constraint propagation. So at each step of the search, we propagate the constraint to reduce, to filter the search space. And what is difficult is that if we have a large number of time steps, the propagation slows down because it has to consider all time steps. So Penelope has developed new propagation algorithms which scales much better on this kind of data. And she also has integrated some reasoning about precedents and successors, which I'm not going to detail here because it's a bit technical, but we have a paper on that point if you're interested. And well, I just give the result here. We have here two different benchmarks. And we compare the time needed with the classical CP, and now the time needed with the new constraint, the new propagation, which is called TD, no overlap. And so if we are below this this line, it means that we win some time. So we can see, well, these instances are smaller than this one, and the larger the instances are, and the more the gain is with the new constraint. And on average, well, the new constraint allows us to compute tools which are 20% better than previously on a fixed time. We fixed the time, I don't remember, maybe 5 minutes, and then we will look which one is the best one. And so it's always TD or no overlap, which is quicker.
And the 5 minutes are determined by expert knowledge?
It's this is used by transportation professionals.
Okay.
And well, this is the time that
they assume that this is a pertinent time.
This is a parameter. They just tell us how long they agree to spend on this computation. Well, this problem is NP hard. So as soon as the problem is big, we know that we cannot prove optimality of so the solver. We have to stop the solver. But the idea is to find the best solution within a given amount of time. I don't remember exactly what was the limit, the time limit for this. Okay. So now we can skip to the next challenge. Okay, now we are able to quickly compute time-dependent tools. The next challenge is that, well, these time-dependent tools, we compute them the day before doing the delivery. And we use historical predictions. We use predictions which are based on historical data. For example, if we know that tomorrow will be a Monday, then our time-dependent predictions are computed on last Mondays, and we use these predictions to build our tool. But now, when we are so the tool is this one, and in real time, well, the truck has left here, and the truck is maybe it is here, and then in real time, sometimes it may happen an accident, and the real traffic conditions are different from the predictions. So we have in real time to react and to adapt the tool. So in this case, instead of simply computing a new shortest path and keeping the order, if we do that, well, all the traffic jam will stay here. So this is not a good idea. So if we can have reliable short-term predictions, which tells us, well, all here, it will be a mess, because when you have an accident all around, it's really bad conditions. So instead of simply doing this, we completely recompute a solution. Of course, we have to take into account, for example, the payload, the fact that in our truck, well, there is. I'm sorry, my English is not very good. It's difficult to say things. So we have loading constraints in the truck, and maybe there are some very heavy things just in front of the truck, and we cannot change everything. So we have to take this into account when we recompute a new tool. So we take these constraints into account, and we propose a new route. And this new route propose, for example, first to deliver this point, and then this one, and finally we go back with, well, all these points, there is no change. So what is difficult here? Well, the first point is very important. We need to have reliable short-term predictions, and this is difficult. That was a goal of the Optimod'Lyon project. So we have 1 hour short-term predictions, which are quite reliable now, but we are still working on that point, and this will be the next part of my talk. And the second thing is that we need to do this optimization in real time. And actually, we have realized that it's, and this will be the third part of my talk, we have to be able to anticipate a little bit. Well, we cannot anticipate accidents. This is not really possible. But if we look at probability distributions, we can notice that in some places, it's quite usual to have unexpected events, and there is well, a very large variability of the traffic conditions, whereas on some other roads, it's nearly always the same values which are measured. So we have to anticipate this, and this will be the third part of my talk about stochastic optimization. So we are going to try to anticipate likely scenarios to compute what we call flexible solutions. And a flexible solution is a solution which can be very easily adapted to likely events. So now, first, the short-term predictions, and then we will see a stochastic optimization. So this is the Astral project, which has just started well, in November 2014. It was, I don't know, five months ago. It is founded by IMU. IMU is Intelligence des Mondes Urbains. It is a kind of very big project, 10 years project, all about cities and smart cities. So this is a collaboration with, so this is my lab. The LET is Laboratoire d'économie des transports, so it is economy on transportations. And LICIT is a lab on transportation. It depends on IFSTAR. This is a French, this is the equivalent of the CNRS, but for the transportations. And finally, the Grand Lyon, which provides us the data. So we mainly have a funding for a PhD thesis. So Julien has started 5 months ago. So this is ongoing work. We are starting working on this. Our goal is to learn predictive models from traffic data. And we want to use this model to compute multimodal routes and compute, here is what we call an accessibility maps. The idea is to show people the time it takes to go from one point to other points. So we fix the starting point here. It is a map of Lyon. It's not very easy to recognize. Here you have La Gare de la Pardieu, which is, well, the center of Lyon. And it shows you in 5 minutes what regions you can reach. So in 5 minutes, you can go anywhere in the red region. And then in 10 minutes, you can go, well, I say 10, but I don't remember if it's 10 or something else. You can go there, and in 15 minutes, etc. And this is an accessibility map which considers, I think this one is with public transportations, and that's what you can skip here, or here, for example, because with public transportations, sometimes you can go very fast on some points which are far. So this kind of accessibility maps is used to communicate with the population and show them, well, you can compare different kinds of transportation. You can have an accessibility map with public transportations, and you compare with an accessibility map with bicycles and an accessibility map with your personal car, and you can see, well, finally, maybe with public transportations, if I want to go from here to here, it's faster than with my, my personal car. And the focus of all this work is on reliability. Predictive models tells you, well, it will take maybe 10 minutes to go there. But maybe from one day to the other, it is always 10 minutes, or maybe in some other cases, well, maybe it is 5 minutes or 20 minutes. So we want to know if the prediction is reliable or not. So first, what is the data we are working on? This data has been provided by the PC Twitter, which is the people of the Grand Lyon who are working on the traffic in all the Grand Lyon. So we have met them. They have a big room with a lot of cameras, and everything is supervised on this room, and they have a lot of data coming from, well, they have sensors, more than 600 sensors, and these sensors measure two different things, the flow and the occupancy rates. And you can use these two data to estimate the speed. And we use this fundamental diagram because actually you can, here you have the flow and here you have the speed. And when the flow is very low, it either means that well, there is a traffic jam, so you are stopped, or it is maybe because there is no traffic jam at all, so you run so fast that, and the flow is very low. And so we only measuring the flow is not enough, and only measuring the occupancy rate is not enough. But if you have both the flow and the occupancy rate, then you can estimate the speed. So we have these two different measures for 600 sensors, and we have one measure every 6 minutes, and we have this data for the last 6 years. So we have a lot of measures. This is not really big data. I'm aware of that, but we are quite happy to have all this data. And we are trying now to analyze this data and to use it to build predictive models. So just to give you an idea of what is this data, I consider 4 different days here. So we have 4 days. Up are the flows and down are the occupancy rates for 2 different sensors. It's sensor 1 and sensor 27, sensor 1 and sensor 27. So we can see that, well, the data is, there is a lot of variations, and sometimes there are strange points. Not sure I have strange points here. But maybe, for example, here, when we have just a peak on the occupancy rates, sometimes we have peaks because a car just stopped somewhere and the driver leave the car to buy cigarettes or bread. And so we have strange peaks sometimes. So we have to deal with this kind of data. Now this is, we are just starting this work, but I'm going to just tell you the first results we obtain. So the first question is how to build good predictive models for this time series. So these are time series, okay, because we always have time here, and so we have different values. Well, the values vary with time. So there exists quite a lot of models to analyze time series. So the first question is, can we use linear models, or should we use non-linear models? If you look at the literature, maybe non-linear models should be better. So we are investigating both. Now, the second point is that we have measures from different sensors, and we would like to know if there is a dependency between the sensors. Well, of course, the answer is yes. We know that if there is a traffic jam somewhere, it will have an influence on the other sensors, but actually we don't really know which sensors influence which other ones. So we have to learn this dependency. And once we have learned it, we would like to know how to integrate this dependency information in our model. So right now, we are comparing two different models. The first model is a very well-known one. It is called Starryman. It is a linear model which exploits spatial information. And it's also a multivariate model in the sense that it considers a set of sensors which are dependent. But this means that we must know the dependency between the sensors, which is not so easy to give. But we are. So this is our first model. And the second one is a very simple model, which does not assume that the data is linear. We simply search for similar sequences in the past, and this allows us to predict the next value. So we don't assume that it is linear, and we combine this with smoothing because, as you can see here, there is a lot of variability, and if we look in the data, in the past data, we will not find this variability. So we have to smooth the data, and we use a nonlinear model to smooth the data, which is TZN. And this model, which is not linear at all, it is univariate in the sense that we do prediction for each sensor separately, because we don't know yet how to integrate the dependency information. But we are working on this, and we have a few ideas. So just the first results. These results, well, it's Julien who is doing his PhD, and he obtained them last week. So it's really very new, and well, I'm not going to comment a lot on this. Just to have an idea, we selected a set of sensors for which we suppose we know the dependency because they are all on the same road. So we know, I think this road is in this way and this one is this way. So we know that, well, there is a dependency between all these sensors and all these sensors. So we built a graph here, which corresponds to these sensors. And we give this graph to Starryman. And well, this is just an illustration on one sensor. And from one to the other here, we simply look the dependency for just one sensor ahead. So, for example, if we are interested in this sensor, for this sensor, we only look at these three sensors. And for this one, we have a distance of 2. So for this sensor, we look at all these and all these. And for this, we have a distance of 3. So for this sensor, we look at all these and all these. So when we go down, we have a wider view of the sensors in the neighborhood. And well, the first results tend to show us that finally we have better predictions with just one sensor ahead. But this may be because our dependency, which is kind of naive, because we simply just look at where are the sensors. Well, we obtain better. So the blue line is the real line, and the green line is what we have predicted. And we have better predictions when we look just at one step. It's not. It's worse when we look at better steps, at larger steps. So this is. I'm not going to comment a lot on this because this is very new. Just to give you an idea, and we also have results with the other method, which is non-linear method. And well, again, we have in red, we have the real value, and in green, the prediction. And this is here, this is a prediction with a difference of 6 minutes. Here it is with 30 minutes. And here we try to predict for in 1 hour. So for it's, of course, it's more difficult to predict with what will be in 1 hour than what will be in 6 minutes. But it's not so bad. So now what we have to do is to really compare these two predictions, and we have not done this yet, so I will not present it today, I'm sorry. So now what's going next? Of course, we have to compare our models, and we have to answer, well, what is better, linear model or non-linear model? We have also to have a look of, is it interesting to have this spatial information of dependency between the sensors or not? Also, we want to predict together occupancy rates and flows instead of, actually now we are predicting them separately. And the question we want to address is, are we able to predict the reliability of a prediction? I'm going to illustrate this on. This is from IBM website, and I think it is really interesting figure. Here you have the time of the day, and here you have the duration of a trip. This is a trip to go from IBM Manhattan office to the airport. And depending on the time you leave IBM Manhattan office, well, sometimes every black point is an observed duration. And you can see here, for example, that it is always the same duration, well, or nearly. So if you leave your office at this time, well, the prediction is very reliable. There is no variations. But if you leave your office at this time, the prediction tells you it takes this time, but there is a lot of variability. And you can go much quicker than that, or you can go much longer than that. So at this point, the prediction is not reliable, and you have a very big variation. So the question we want to address is, are we able to exploit this reliability to compute either robust routes? A robust route is a route which will have very small variations, because we will only use sections for which the variation is always very small, well, except if there is an accident, but otherwise we will always use routes for which the variations is very small. So this is a robust route. And flexible routes, this is a very different kind of solution. A flexible route is a route of, okay, we can use sections for which we have very big variations, but we have computed alternative solutions for every possible, well, not every one, but the most probable, but we will have a second, so I will explain on the next slides what is a flexible route. But maybe you catch my point? Yes? Okay, so I don't have to explain it. So now this point is about stochastic optimization. So now, instead of looking at average values, we are looking at probability distributions, so that we can use all different possible realization to compute flexible solutions. So this work is done in collaboration with Louvain-la-Neuve, which is in Belgium. This is close to here from a Brazilian point of view, but from a French point of view, it's quite in the north. But it's a very nice place. And so this is joint work with Yves Deville, and this is the PhD thesis of Michael Saint-Villain. So now we are looking at stochastic data. For example, the predicted duration to go from one point to the other, we can look at it at stochastic data. And in classical optimization, we only look at average predicted data, and we are not able to anticipate on the different likely events. Whereas if we look at the stochastic data, now we look at probability distributions so that we can compute flexible solutions. And a solution is flexible if we are able to adapt it very quickly to the different likely events. We have, well, at the beginning of the PhD, we asked Michael to have as application our delivery problem, and the stochastic data was the durations to travel from one point to the other. But it was a bit difficult for him because we don't have yet the data, all these probability distributions for the durations. We don't have all of them, and it's too difficult. So it chosen another application, but which is quite similar. This is on-demand transport. We have this on-demand bus. I don't know if you have this in Brazil, but in Europe, in many cities now, you have, for the suburbans, you have buses which are public transport. But during this time window at this point for going to this point. And when you phone, the person must answer you quite immediately, okay, we can accept your demand, or no, it's not possible, we have to reject it. Okay, so this is this on-demand bus, which solve what is called the last kilometer problem, because the public transport go in the city, and then if you live a bit farther than just the city, you need this on-demand bus. And another application is the same-day deliveries. This is, well, eBay is doing that, so this is a photo of eBay. Now you can phone, or well, it is with internet. You do you command things, and you can have your command which is delivered the same day. So if it is delivered the same day, again we need on-demand transport to do this delivery on the same day. And when you do your command, the system will answer you, yes, it's possible, or no, it's not possible. No, it's not possible. So in this slide, I'm going to explain a bit more what is this problem. We have some vehicles, and each vehicle has a limited capacity by means of the number of persons which can go in the vehicle, or the number of colis. Parcels. Okay. You can pack in the vehicle. And that now, so each vehicle has started its tour. For example, here I have three trucks, and each truck has started its tour. And well, this one has already delivered this point and this point. This one has already delivered this point and this point, and so on. And the demands are revealed during the day. Some demands are already known. These are the green points. The green points correspond to known demands, and all gray points are demand which has not been done, but which may be done. We have, for each green point, it means that it is possible that somebody will ask something here, but we don't know yet. Maybe it will be yes, maybe it will be no. And during the day, some demands arrive. So this is an online request for this point and for this point. So here I have somebody who has just called and said, is it possible to come and take me during this time window? And here it is the same. So for each demand, we have to take a real-time decision, and we have very short 5 seconds to answer. because, well, the person does not want to wait for the answer. So in 5 seconds, we have to take a decision, which is either we accept it. This is the case for this demand. It is accepted. And if it is accepted, we must serve it. That is, we must ensure that there exists a possible tool, which still delivers the other accepted demands, and which also delivers this one. And if we think it is not possible to serve the demand, then we reject it. But of course, our goal is to minimize the total number of rejected demand. And this is the total number of rejected demand at the end of the day. But when we take the decision, we don't know all the demand that will occur. But if we don't know all the demand, we have the probability distribution of all these demand. Here, we know that, for example, the probability is very low, and here it is very high, I don't know. And so we have to guess on the future. Now here, I'm not going to enter into the details, I don't know.
So you have enough time.
I have enough time, but I'm not going to enter a lot into the details because I think it's not really interesting here. Again, we have a paper with all the details on that. Just to give the idea of how we do this. So each delivery point here, for each point here, we have a stochastic variable, and we have knowledge on this stochastic variable. We know the probability for each point that a demand occurs at a given time. So we have random variable vectors, which are noted like this. And so this random variable is realized to 1 if there is a request for the point I at time t, and it is equal to 0 otherwise. Before time t, we just know the probability distribution. And after time t, of course, we know if it has been realized to 0 or to 1. So at each time, if I am at time, here is time 0, so before, I just know all the possible things. And then at time 1, there is one realization. I know that, well, the truth is this one. And at time 2, I know that the realization is this one. But then at time 2, okay, I know that this is what happens. But then I have all the possible values for the futures. But for each possible value, I know its probability. So I can try to find the best possible solution, which we call the flexible solution. And the idea will be to minimize the expectation for all the possible scenarios. So what is a scenario? Sorry. What I call a scenario is a realization of the random variable. So for example, here in green is one possible scenario. But of course, I have an exponential number of scenarios because for each possible value here, again, all these values are possible, etc. So I have an exponential number of scenarios, and one scenario is one possible realization. And each scenario has a realization probability. Now, the solution is in 2 steps. The day before, the day, I am going to compute what I call some useful stuff, and this is offline computation. The day before, I know some requests, which are called offline requests, because some guys have asked for a delivery the day before. So some requests are already known. So I can prepare a first solution with this known request. But I am also going to anticipate with respect to the probability distributions of all the other possible requests. And then during the day, this is online computation. And we are going to optimize our solution during the whole day. And we have discretized the time. So we have time steps. And so at each time step, there are some online requests which are revealed. And for each online request, I have either to accept it or to reject it. But as I have prepared many things with respect to these possible requests, I will very quickly answer. And so to very quickly answer, I will use a decision rule. And actually, this is our real contribution. This is the goal of the PhD of Michael, is to design this decision rule, which is able to choose an action for each online request and say either accept or reject. And if we say accept, we have to give the tool which actually allows to accept it. And so we do this at each time step, and we use the remaining time between two time steps to try to improve our all possible solutions using the probability distribution. So I'm not going to enter into the details, but just give an idea of this decision rule. This decision rule, we are at time t here, and we are going to solve what we call a multi-stage stochastic problem, because at each further time step, we have to anticipate all possible scenarios. And what we want is to minimize the expectation over all possible realizations. That is, over all possible scenarios. But of course, there is an exponential number of scenarios. So a subset of scenarios which all have the same probability, and we assume that these scenarios are representative of all the possible scenarios. The larger, if we have a lot of scenarios, it will be representative. If you have not a lot of scenarios, it will not be so representative. So we try to have quite a large number of scenarios. And then we have to find optimal tools for all possible scenarios. And this problem is the vehicle routing problem. And this problem is NP hard. So we cannot solve it at optimality. So we approximate it and we use local search. And this is the last slide, which is well the same as previously, but I just complete just to explain that now we work with a pool of scenarios, which is a sampling of all possible scenarios. And what we do here is that we compute a good sequence of future actions with respect to the offline requests, which are the requests that are already known, and with respect to our pool of scenario. And this is done with local search, and we, at regular times, we update this scenario pool, we remove some scenarios, and we generate other scenarios, and this ensures diversity in our search. This ensures that we will have, well, we hope we have a good view of what can happen in the future. And so this is the day before, and then during the day, online computation, again, at each time step, well, we have random events which are realized, so we update our scenario pool because maybe some scenarios are no longer possible, so we remove them and we generate new scenarios. And for each online request, we accept or reject it using our good sequence of future actions. And so this is the decision rule. And now we use the remaining time to again improve the sequence of future action with local search. And we periodically refresh the scenario pool by removing some scenarios and generating new scenarios. So I'm not going to enter into the details because it's quite technical, but if you're interested, I can send you the paper. And just very quickly, the experimental evaluation. So we have considered a well-known academic benchmark for this problem. This benchmark allows us to control the degree of dynamism of the the instance. For some instance, there are a lot of demands which are not known in advance. For example, in some cases we don't know any demand in advance, and all demands are done during the days. Whereas in some other cases, well, we have 44% of the demand which are known before starting the delivery, and the other demands are arriving during the day. And here I just give the gain of using our approach with respect to not knowing anything on the probability distribution. So if we know the probability distribution, well, we can have a gain from 20% to 65%, and the gain is in the number of rejected demands. It means that here we are rejecting 19% more demands if we don't know anything on the probability distribution of the demands. And if we use this knowledge, we can accept more demands because we have anticipated all possible demands. So this is, I'm not sure you have this kind of data, but actually we really would like to evaluate this on real world data, and we don't know where to find this data. So this is the end for me. Time for question. I just have kind of summarizing all this. Well, we are developing new tools to analyze the data which is monitored by sensor networks. This is not really big data, but starting to become big data. Actually, it is incomplete and not reliable, that's true. And we have new tools to solve constraint optimization problems, and we have different kinds of constraints. We try to scale with respect to time-dependent costs, and also we try to take into account stochastic knowledge. And well, these tools are developed in the context of constraint programming, so they are generic, and we can easily use them for different applications. This is a pluridisciplinary work. We are working with people in transport and in economy, and in our lab we are also using machine learning, data mining, constraint optimization, and we mix all this. Okay, if you have any questions. I really apologize for my English. It's difficult to speak in English.
That's great. Thank you. There's room for questions. I have a few questions online. Maybe I can start with the online questions while you think about them for your own. So I have one question here saying, have you compared your tool with existing apps like Google?
Google.
I mean, I suppose that they do not say.
There is OR tools for developed by Google. Is it this?
I suppose it is.
No, we haven't, but we could. But they use quite the same. Well, they use constraint programming. I think that the official name of is OR tool of Google, and well, they use constraint propagation. We could compare with them. We have not yet.
Thank you very much for your very interesting talk. I'm from Japan, actually. I'm currently spending some months here. My question is not very technical, but I'm very interested in the project funded by Lyon.
Optimod'Lyon, you mean?
Yeah.
Grand
Lyon.
Yeah.
Yes. Is there actually the specific goal given by the municipal or government? For example, Grand Lyon want to reduce 20% of traffic jam, or they want to reduce the pollution or something like that. This kind of goal.
I'm not sure it has been quantified 20% or things like that. But it is clearly the goal is to reduce the traffic jams and to reduce the pollution. This is really a problem. We have the same problem in Grenoble also. These cities, there is a lot of pollution. Well, some days there is alerts for the so clearly the goal of Optimod'Lyon is to try to solve this problem, and part of the project, the goal is to incite the population to take public transportations instead of private cars. So when we compute the shortest path to go from one point to the other, we show that it's quicker with public transportations or with bicycles, because we have many cities in France now, we have these sharing bicycles. So the goal is really to prevent people from taking their personal cars.
Can I ask you a second question? You said that the city provided free services for
Yes,
citizens.
yes.
And do they actually evaluate the effect of the services? Actually, the citizens use the services, and is there a way to evaluate how much effect is given by the services?
It's well, the services are just arriving now. Well, the project will finish in May. And in May, there will be this, for example, this service is tested now, and well, people from the Laboratoire d'économie des transports have made a lot of experiments to see how people react with respect to this application, which is really a nice application because it is real-time application. So you just say, I want to go to this point. I'm here, I want to go to this point. And the application finds the quickest way using public transports, bicycles and things like that. But if finally at some point you are going to miss the connection, then it tells you, hey, be careful, you're going to miss it. So we change in real time the itinerary. And so they have made experiments to see how people react with this application. Well, it was interesting to see that some people were very pleased with this application, and some other people were a bit frightened by the application, because some people don't like to have applications which change its mind and say, well, finally, we are not going to take this, but we are going to do that. and well, actually, this gave us the idea of computing robust. For some people don't like changes. And for these people, we have to compute robust solutions for which it's not likely that they will have to change the solution. And it's a question of age sometimes. Well, old people don't like to have changes. Young people are
very conservative.
So there are some experiments, but it's not yet available for everybody. It will be in May. In May there will be a very big with the mayor. He will use the application and show everybody, well, it's a very nice application, and then we will have. And that's the same for the 1 hour prediction. It's coming, but it's not yet completely finished.
Thank you very much.
You're welcome.
Just to follow the question, in that case, you suppose everybody has the application.
Yes.
So how do you take into account that everybody will use the application, and so you will have congestion because of using the application?
That's an excellent question. Of course, this is a complex system. And if we optimize for everybody locally, we are not going to have a global optimum for everybody, for all the population. Well, this is particularly true for when we give advice to people driving their car. Because if we say everybody don't go there but go there, then there will be a second traffic jam. This is an interesting question, but we don't know the answer yet, because it's really difficult to have a global view and to have personalized advisors which ensure that they will do different things. It's very difficult.
It's exactly the same problem they get in finance, because they have also run the same algorithms simultaneously, and so there are crashes due to just the synchronization.
Yes, well, that was the point in my last slide. I was, oops. That's why I was saying we have to combine these two different scales, individual versus global. This is, I think this will be the next step. We are not yet, and it's really difficult. Even for the deliveries, at the beginning, we wanted to optimize several deliveries at the same time. But it's an even more difficult problem. And finally, we optimize each tour separately because it's easier to do. Once we will be champion for optimizing each tour separately, then we will skip to the next step, which is have a global view and ensure that the global solution is optimal, which means that some individual will have a decrease in their solution quality, but you have to accept it. And we have to work with sociologists and things like that because this will work if people accept it and agree to follow what an application asks them to do. So this is very difficult.
Are you looking at game theory?
No, we should do. Yes, of course. This will be the next step. Well, actually, stochastic programming is already very difficult to handle. So, but the next step is, of course, to look at game theory and to work with sociologue to see how we can. Well, human beings have their own feelings, and they're not always ready to follow what an application tells them to do.
I have two questions. One is from University of Las Américas in Mexico.
Oh.
So they say the computations seem costly. Could you gain if they were done in parallel infrastructures? And could you comment on big data volume and velocity with respect to your research?
Okay. The first question about parallel computation. We have a lot of work, not me, but many people in OR and constraint programming work on this. This is not so easy, but we can, well, we don't have linear speedups. When we use n computers, we don't go n times quicker because we lose a little bit. But there are a lot of, yes, of course, there are a lot of people who do that. Anyway, if you have an NP-hard problem to solve, even if you have 1,000 computers, it will not change a lot. The fact that it is NP-hard. We need an exponential number of computers to become to solve in polynomial time. So that was the first question about the big data. There were 3 parts in my talk, and here we don't have big data. Here we have predictions which have used big data to do the predictions, but now then the prediction is on normal data. We have a few hundreds of delivery points, and that's all. So this is not big data, but we have computational issues because the problem is NP-hard. And even, well, a delivery with, well, even 50 points, it's difficult to solve optimally. But we can solve with a good, we can find good solutions in, well, 1 minute we already have a good solution, so it's okay. Then here we can say we deal with kind of big data, because now we have all these sensors, and each sensor gives us a value every 6 minutes. But I'm not sure this is very big data. It's just, well, we have data flows.
Well, it's continuous.
It's continuous, but it's not big data. So I don't like using the word big data, and I don't think that this is really big data. But we have computational problems because here and here, in both cases, we have NP-hard problems. So that's why it's difficult to have.
I'm going to ask another question, and then I will let you ask more questions if you have. So this is from, again, from Puebla. This is another institution, Tecnológico de Puebla, and they say, can automatic learning be applied for dealing with previously computed scenario plans?
Use machine learning to.
They say in the last problem, I suppose.
Yes, this is a good idea. Yes, we could or use some kind of case-based reasoning to reuse previously computed solutions. I guess this is what it means. Yes, this is a good idea. We have not thought it yet, but thank you.
I will go. Well, they are watching you. And I have others, but I can let people if you have other questions here.
I have one more.
Go ahead.
In the first problem, so the criteria you want to optimize was the length of the tour in terms of
the duration of the tour.
But it depends also in the periods in which you can deliver.
On the time windows.
So yeah. How do you include the costs due to not delivering?
We cannot not deliver.
Yes,
these are hard constraints.
System. So you in sometimes you cannot because you are late.
Well, okay, you're mixing stochastic. Well, I have separated them, but
how do you put this constraint in fact in the
we don't.
Optimization function?
We should, but we don't. In this work, we consider that these time-dependent predictions are reliable. But if in real time, finally, it occurs that one prediction was completely wrong, then we recompute a new solution. But we don't mix this and this. Well, the ultimate goal is to do stochastic optimization on this problem too, in order to be able to anticipate the likely events. But we are not doing it yet. That was the initial subject of the PhD of Michael, was that. But then he went back and said, it's too difficult. And I agree, it's too difficult. So it's easier to work on demand because we have smaller number of random variables. Here, if we do that on this problem, the random variables are the durations on the sections. So we have a huge number of random variables, and it's even more difficult. So we are starting to experiment on an easier problem, and then the ultimate goal is to combine, of course.
And because when you have a large amount of variables, you can perhaps have approximations like mean-feeds or other techniques are available when you have a huge number of things rather than just one or two critical values.
Yeah, we have to look at that. Well, Michael is well, he's starting this. We still have 3 years, because even 4 years. In Belgium, they have 6 years to do a PhD. So yes, that's great. So he still has 4 years to work on this. And yes, the ultimate goal is to combine with this.
Other questions? I just have one question. if you consider psychological and social elements in the problem, does this mean that you have to add constraints or to have a sociological model or psychological model that should be integrated in somehow in the other?
Well, for this project, we are working with the Laboratoire d'économie des transports. Where is my? Oh, here. Okay, we are working with the Laboratoire d'économie des transports, and they are really interested in personalizing when we compute a route to go from one point to the other. The goal is to be able to personalize the algorithm to the kind of people, and some people don't like risk, and they want to have robust solution that guarantee with a given probability that, well, in 95% of the cases, it will work okay. And some other people want to have the fastest route, and they are okay with changing if there is a problem in the connection. So in this case, they want to compute flexible solutions. So the goal is to be able to personalize the algorithm. So the person will say, well, I don't like risk, or I like risk, and we will compute different solutions depending on the people. And that's, well, the LEDs, they are really interested in that. And including for the accessibility maps, they want to have a kind of button which says, I don't like risk, I like risk. And the personality and the accessibility map will be different depending on the kind of people you are. That's what they want to study.
I'm not the prophet. I have one last question. There are people working with crowdsourcing in order to collect and to have feedback on the applications. How would this be integrated or make the problem more difficult if this kind of technique is used?
This is, we would like to do that. We really need data. Since now we are working with this data coming from sensors, this is the first kind of data. But it would be really nice to have also data coming from smartphones of people saying, well, I am in traffic jam, or, well, everybody has GPS. And we would like to have this data to have more information. But it's not so easy to have this data. Since now, maybe in the future it will be more easy.
And there's also the reliability of data coming from people is less.
Of course. This is a good point.
Thank you very much. Thank you. We have a 15 minutes coffee break before we start the next session. So coffee break is going on downstairs in the parking room. If you want to leave your things here, I'm going to close so that you can leave. Thank you. Thank you for coming. Oh, good. Oh. Okay. Yes.
Provide a kind of general order.
Oh, that's quite interesting. And then during the group, there will be discussions around that. Eventually, we can see how you can collaborate with Brazil. No, I'm Mexican.
I'm also interested in how the connection
Yes, and in fact, there's been a lot of collaboration for years. I work here in France, and then there are a lot of projects, and there's also a laboratory with the south of Brazil, so we're just trying to make things work with the collaboration. Yes, it's during until Friday. You're welcome every day.
Yeah, I'm just very close from here to here, but we don't have the exact matching between. So it's very difficult to reconstitute the graph.
Hola, bonjour.
Maybe we can talk the data,
Yes,
the original data. Maybe it's not. No, it's
merci d'être venu.
Some values are definitely not consistent.
C'est super.
So we have to remove them.
Oui.
There was a lot of problem. I didn't talk about that because this is not my point.
Yeah, this is because for me it was really interesting because I'm not from this area, but then I sent an application and we are more concerned about
Oui, c'est excellent, c'est excellent.
treat
Ouais,
the
oui.
data
En plus, ça
and
open
how to
le
integrate
access,
the
c'est
data.
un grand projet national.
Sensors, but also to have open data, data from web data source,
Oui,
from
en fait, j'ai assisté à
social
une
media, how we can
action.
integrate everything and to
Oui,
produce
oui, oui.
a bunch of data that you can use.
Oui, super, oui, oui, oui. Donc, en fait, nous, comme je t'avais dit, l'objectif, c'est de se connaître, de prendre contact pour voir si éventuellement, soit des petits projets, soit des plus gros projets, on peut répondre à des appels. C'est aussi l'intérêt. Parce que même entre Brésiliens, parfois, vous êtes loin, etc. Et il faut voyager pour se rencontrer.
Que je ne connais pas, pardon, je ne savais même pas ce que j'étais en train
de faire.
Donc,
c'est bien pour apprendre ce qu'il y a en Brésil.
à côté.
C'est bien.
Bon, encore une fois, merci.
Merci.
De vous connaître.
Moi aussi, c'est un plaisir. On fait comme ça, nos ordinateurs sont.
Ah, c'est un amphi.
Oui, c'est un petit amphi, ça va. T'as pas vu quand on a pensé la tête tout à l'heure?
Bah, j'ai pas passé la tête aussi.
Ah, t'as pas passé la tête, t'étais derrière moi en fait, c'est ça?
Oui. Ah, et puis
Alors.
on est filmé. C'est en vidéo, enfin, c'est diffusé au voisin.
Ah oui, non, mais s'il faut mettre le texte.
Ah, est-ce qu'il faut mettre dessus?
Et moi, il faut alors dans ce cas-là, il faut faire un PDF. Parce
Mais
que
pas
sinon,
sûr.
ça va pousser, ça va sauter. Ah!
Bah
Tu
non,
crois?
parce que c'est pointé sur l'écran.
Hein? Tu penses qu'il suffit que je me mette là?
Brancher électricité.
Là, c'est quoi là?
Là, c'est quoi? C'est la vidéoconférence. Là, tu fais coucou au Brésil.
Ah, c'est branché sur l'écran. Donc moi, si je projette sur
Non,
l'écran, c'est
branché
bon.
sur l'écran. Oui, oui, oui.
D'accord.
Ça filme l'écran.
D'accord.
On va les animations en plus, c'est pas.
On n'a pas fait d'animation. Con, celui-là.
Je sais même pas pour qui.
Ah, t'es déjà allé au Brésil?
Non.
Hmm.
Je vais jamais aller sur le continent.
Ah, oh là là, qu'est-ce que c'est super bien. Ah, mais il reste une prise, hein. That's good.
J'ai fait que le continent asiatique.
Ah ouais, alors moi, par contre, c'est l'inverse. Je suis jamais allée. Et ça, le problème, c'est que ça m'attire pas. Ça me fait peur.
Moi, j'y ai là combien?
Non, mais toi, c'est normal, c'est pas pareil. Mais moi, je trouve que c'est tellement différent que ça me fait peur. La culture est tellement différente.
On a un
Dis-moi.
canal YouTube. Donc on va, si ça te dérange pas, on va te filmer parce qu'il y a super expert.
Non, mais il n'y a pas de souci.
Super.
Pas de souci.
Vite fait à Lyon. Tout donné,
Pas de
vous
souci.
avez donné un cours.
Donc en anglais, hein.
C'est-
Donc comme ça, je vais parler plus doucement.
Donc,
Parce que j'ai tendance en français à être
Ah,
rapide.
speedy.
Et on fait la présentation tous les deux.
Super.
Bon, je vais
Oui,
commencer,
oui, oui.
faire la première moitié, il fera la deuxième.
Mais pas
Très
rester
bien.
longtemps.
On travaille vraiment tous les deux en binôme.
Super.
Je pars début d'après-midi.
bonjour.
Bonjour. C'est Javier,
Salut,
c'est ça?
Tout à fait, c'est bon. Enchanté.
Sylvie?
Donc voilà. Et comment tu vas?
Ça va bien, ça va bien.
Ta fille?
Bien. J'ai un fils maintenant.
Oui,
donc,
la note.
dis donc, ça fait un moment. Et là, attends, elle a quel âge maintenant? 3, 4?
Ma fille,
Ta
5.
fille. Mince.
Non, t'es pas loin,
Et
franchement.
voilà, donc
Même
quand
moi
même.
qui suis à côté, des fois, je me rate de 2 ans. Alors franchement, bravo.
Donc, ouais, c'était pas là. Il y a 5 ans, t'imagines? Oh, c'était la dernière fois que j'ai.
Bah,
On l'a
Max, ça
vu,
fait un moment.
c'était. Oui. Et on était quoi? À Autrin?
Ah, au train, oui, je pense, mais c'était au bon milieu du projet.
Oui.
C'est 2006 ou 2007.
Ouais.
Donc, c'est un fils. Il a quel
T'as
âge?
vu, hein? Tu vas voir, ça va aller de plus en plus vite.
Voilà, quand même.
Il me croit pas que le temps va
Il est
descendre.
jeune. Il s'appelle jeune. Bon, il s'appelle comment?
Naël.
Naïl. Donc, et ta fille s'appelle?
Zoé.
Zoé, s'appelle.
Il est grand.
Eh oui, tu vois. Et tu me diras la prochaine fois si c'est vrai cette histoire qu'il pousse vraiment vite hein, ou s'il pousse lentement.
Je viens de me souvenir d'un truc. Il faut aller en plus pour acheter les
Les cordons, les
Ouais.
boutons,
voilà, c'est-
les lasers.
Ouais,
Ok.
on est au café.
Je peux aller. Bah,
Ça, c'est bon. Alors, vas-y.
Je tente le branchement.
c'est mal déjà, on s'en va
C'est là.
C'est déjà ça.
Hein? Ah, ça arrive, non?
Ah oui.
Yes, good.
Ouais, mais c'était.
Alors, ensuite,
Non.
là, est-ce que j'ai un truc qui marche? En général, ça marche pas toujours.
Moi, il faut que j'aille manger des pains au chocolat, sinon je vais pas tenir.
Good. Allez. C'est tout
Du coup,
bon.
il n'y a pas besoin de micro, c'est bien.
Hein? Non, il n'y a pas besoin de micro, c'est bien ça. Alors,
Ok, quanto strade?
allez, on va voir les doucement. Hein.
On laisse les affaires là.
Bon, la veste, je pense que c'est bon, non? Ouais, je pense quand même. Il faut laisser la machine là pour lui.
Je vais fermer.
Tu vas fermer.
Necesito las llaves del auto.
Ouais, trop café.
Y además me regañó tanto como por qué me da un número de teléfono que no contesta. Me puede dar el del papá, pero si no contesta. Y le volví a hacer igual como le dije al rey. Escribe mensajes. A ver, ya. Silencio. Le di mi número de teléfono. ¿Cómo? Se te cayó el cable.